Hello, everybody. Today we're actually starting Honors Pre-Calculus Unit 2, Analytic Trigonometry. Now, I can't tell you how much I love this unit. I think I love this unit a whole bunch because I love puzzles, and I feel like this whole unit is just one big puzzle. So today we're actually going to start talking about using fundamental trigonometric identities. Several we've already gone over. So some of this will be a little new, some of this will be a little reminder. So the first thing I want to talk about is the fundamental trigonometric identities. Now, the first identities that we have are the reciprocal identities, and these should look familiar. We have sine of u is 1 over cosecant of u. That's because sine and cosecant are reciprocals, which also means that cosecant of u is equal to 1 over sine of u. Cosine of u is equal to 1 over secant of u, which means secant of u is 1 over cosine of u. Tangent is 1 over cotangent, and cotangent is 1 over tangent. These should already be in your memory. In your brain, okay? These should already be there. So, we also have the quotient identities, which you guys may have already figured out. We know that tangent is y over x, so it makes sense that tangent is sine over cosine, because remember, sine is y and x is cosine. And if tangent is sine over cosine, it makes sense that cotangent is cosine over sine, because tangent and cotangent are reciprocals. Okay, so we also have the quotient identities. Something that is a little bit new is Pythagorean identities. Now, how do we get the Pythagorean identities? Well, we have sine squared u plus cosine squared u is equal to 1. And if you think about it, in a unit circle, we know that x squared plus y squared is equal to 1, where cosine is x and y is sine. So this doesn't come out of left field. Now the question is, how do we get these last two? Now, in order to get the last two Pythagorean identities, what you're actually going to do is you're going to divide the entire identity by either sine squared or cosine squared. Let's do that off to the side over here. So we have sine squared of u plus cosine squared u is equal to 1. Now, what happens if we divide both sides by sine squared u? Well, let's think about it. Sine squared u divided by sine squared u is just 1. Cosine squared u divided by sine squared u, well, we know that cosine over sine is cotangent, so cosine squared plus sine squared over sine squared has to be cotangent squared u. And of course, 1 over sine is cosecant, so 1 over sine squared has to be cosecant squared u. And this is actually this guy right here. Now, how do we get the middle identity? Well, we're going to divide both sides this time by cosine squared u. So we have sine squared u plus cosine squared u is equal to 1. We're going to divide both sides by cosine squared u. Okay, so sine squared divided by cosine squared, sine over cosine right here is tangent. So sine squared divided by cosine squared is going to be tangent squared. Cosine squared divided by cosine squared is just 1. And 1 over cosine we know is secant, so 1 over cosine squared has to be secant squared. And there is our third one. So, like I said, you can kind of get from one to the other by using your puzzling skills. Now, there's also cofunction identities, and I think a lot of you guys noticed that when you were graphing sine and cosine, that you can get from sine to cosine just by shifting it left or right, pi over 2 or 90 degrees. I think this is actually a little confusing for a couple kids because, especially on the test where it was just shifted over, you guys thought it was a sine graph. So it holds true that sine of pi over 2 minus u is equal to cosine, and it's also true that cosine of pi over 2 minus u is equal to sine. But also we can apply that to our other trig functions here. So tangent of pi over 2 minus u is equal to cotangent, and you can actually get back from cotangent to tangent by doing pi over 2 minus u. The same can be said for secant and cosecant. Okay, so these ones are new, very new. The last one I want to talk about is even and odd identities. Now, in Algebra 2, you guys should have talked about even and odd functions. And if you guys remember, you'll remember that f of negative x, if that equals positive f of x, it is an even function. And if you put in negative x in for all your x's and it gives you negative f of x, that's going to be an odd function. What does this mean graphically? Well, an odd function is when the graph can actually rotate about the origin. So for example, if we look at a sine graph, you see here that we can actually rotate it about the origin and it will give us the same graph over and over again. In opposition to that, we have cosine, which looks something like this, right? And this is actually able to reflect over the y-axis. So odd functions rotate about the origin, even functions are reflections across the y-axis. And if you look here, sine and cosecant and tangent and cotangent are all odd functions. And if you look at cosine and secant, these are even functions. But the most important part here is if you look at this negative u, it comes to the outside, and with this negative u for the even functions, it goes away completely. We're going to be using plenty of examples of this, so if you have no idea what's going on right now, that's 100% fine. I'm just explaining how to read some of these identities. So there are 4 ways in which the fundamental trigonometric identities can be used. And today we're going to talk about the first 2. We're going to be talking about evaluating trigonometric functions and simplifying trigonometric expressions today. Tomorrow, we're going to be talking about developing additional trigonometric identities, and later on, we're going to be talking about solving trigonometric equations. Okay, so the first thing we can do here is evaluating trigonometric functions. And what we're going to do is we're going to look at tangent of theta is equal to 2/3, and we also know that secant is greater than 0. Now, we want to find all 6 trigonometric functions. That's what this is telling us to do. The easiest one to find is obviously cotangent, because remember, cotangent is just the reciprocal of tangent. And just like that, we're 1/3 the way done with everything we have. Okay, so again, I want to evaluate these trigonometric functions using identities. So what I'm going to do is I'm actually going to use the Pythagorean identity 1 plus tangent squared theta is equal to secant squared theta. And if you remember, that is our second Pythagorean identity up above. So now I know what tangent is. We have 2/3 squared is equal to secant squared theta. Okay, so now we have 1 plus 4/9 is equal to secant squared theta. We're going to find a common denominator. That's going to be 9/9, and 9 plus 4 is 13/9. So to solve for secant, we're going to take the square root of both sides. So we're going to get secant of theta is equal to the square root of 13/3. Square root of 13 is square root of 13, and square root of 9 is 3. Now, from above, we remember that secant is greater than 0, so we know that this is positive root 13/3. Now, because we have secant, we can also now find cosine, right? So cosine of theta is going to be 3 over the square root of 13. And we're going to rationalize this by multiplying the top and bottom by root 13. So we're going to get 3 root 13/3. Okay, so you now have 2/3 of your problem solved. Now the last one we have is we have sine and cosecant. So in order to find sine and cosecant, what I'm actually going to do is I am going to use sine squared theta plus cosine squared theta is equal to 1. Okay, so now I am looking for sine squared. I know what cosine is now. Cosine is 3 root 13/3. And I'm going to square the whole thing. Oh, this is over 13. So sorry about that. And then that's going to be equal to 1. Okay, so what we're going to do now is we have sine squared theta, and then we're going to square everything here, and we're going to get 9 times 13/169 is equal to 1. We're going to reduce that a little further. 3 goes into 169 13 times, so now we have 9/13 is equal to 1. We're then going to move our 9/13 to the other side, so we have sine squared theta is equal to 1 minus 9/13, and that's going to give us sine squared theta is equal to 4/13. And we're going to take the square root of both sides. So now we have 2 over the square root of 13, which we have to rationalize to be root 13/root 13. So we're going to get 2 root 13/13. So there is sine. Now to find cosecant, instead of rationalizing this again, we can actually go back to this right here and then just flip that to get root 13 over 2. We now found all 6 trigonometric functions. Okay. What else can we do? We can simplify trigonometric expressions. And again, this is my favorite part here. I just like taking these and simplifying them. I know it makes me a little strange, but so here's some hints to solving these. First thing we're going to do is we're going to look for any identities, anything that kind of comes out, or anything we can factor. This is why you had a factor in your prerequisites. Or as your kind of like a last case scenario, we can turn everything into sines and cosines. So if we look at our second example here, tangent times cosecant x. Now, there's nothing that repeats here, so there's nothing like we can pull out, nothing we can factor. There's nothing squared here, no obvious reciprocal identities or anything like that. So we're actually going to have to turn everything into sines and cosines for this one. So using the quotient identity, sine of x over cosine of x is equal to tangent. And cosecant is 1 over sine of x. And if you look at this, there's a sine in the numerator, sine in the denominator. They cancel out, so you have 1 over cosine. And what's 1 over cosine? Well, we can use the reciprocal identity. 1 over cosine is secant of x. And that is the most simplified version of tangent x cosecant x. Okay. Let's look at number 3. So you have sine x cosine squared x minus sine x. Now, the first thing I see here is they both have a sine of x. So what I'm actually going to do is I'm going to factor out a sine of x. Remember, factor basically means you're pulling it out, you're dividing out sine of x. So both terms have a sine of x. So I'm going to pull that out. And then after you do that, you're left with a cosine squared x. And then sine of x divided by sine of x is going to be 1. Okay? And once you see cosine squared x minus 1, I hope that you guys think there's a 1 and there's something squared there. I want to look at the Pythagorean identities here. So if you look, you have sine squared plus cosine squared is equal to 1. Okay? So I'm going to put this in a little bubble over here. We know that sine squared x plus cosine squared x is equal to 1. So if I want to get something that looks like cosine squared x minus 1, I'm going to have to subtract 1 from both sides. So now I have sine squared x plus cosine squared x minus 1 is equal to 0. And then if I want to get this by itself, because it's over here, I'm actually going to subtract sine squared x from both sides. So now I get cosine squared x minus 1 is equal to negative sine squared x. So using the Pythagorean identities, I can say that this whole thing right here is equal to negative sine squared x. We're almost done because you have sine x, sine squared x here. When you multiply x times x squared, if you think of it from that perspective, this is going to be sine cubed x, and don't forget that negative. So this whole thing right here reduces down to negative sine cubed x. Okay, now let's look at number 4. Number 4, we have cosecant x minus cosine x cotangent x. Now, there's a lot of c's in there, but we can't factor anything out, guys. These are all different functions. Okay, there's no obvious identity, like there's nothing that just cancels out. There's no squares, there's no ones. We know there's no Pythagorean identities involved. So the last thing we have to do, again, is we're going to turn everything into sines and cosines. Now, guys, you can solve everything by turning everything to sines and cosines, but sometimes it just really helps if you don't do that first, if you look for other things you can do. Because if you have a lot of sines and cosines in there, sometimes it can get very confusing. But because we have nothing else to do here, we have to turn everything into sines and cosines. So cosecant is 1 over sine of x. Cosine is just cosine, guys. You can't do anything. You can't turn cosine into something more cosine-y. Okay, and then cotangent is cosine x over sine of x. Sorry, there was somebody very obnoxious outside. So now I have 1 over sine of x, and I'm going to multiply these guys together. Now I have cosine squared over x, sine of x. Now, lucky for us, we already have the common denominator. So now we have 1 minus cosine squared x over sine of x. Now, what is 1 minus cosine squared x? Well, again, we can kind of think of it as a thought bubble here. I'm going to have to erase it, though, for the next guy. Okay, we know that sine squared x plus cosine squared x is equal to 1. So if I subtract cosine squared x from both sides, I'm going to get sine squared x is equal to 1 minus cosine squared x. So we know that 1 minus cosine squared x is just equal to sine squared x. So this gives us sine squared x over sine of x. And just like x squared over x is equal to x, sine squared x over sine of x is just equal to sine of x. So this big blob of everything up here has now been simplified to just one trigonometric term. Okay, which is the whole point of being able to simplify these. So in this one, we have cosecant x over 1 plus cotangent x. Now, in the denominator, we have a 1 and something squared. So when you see 1 and something squared, I want you to start thinking Pythagorean identity. Okay, so let's see what the Pythagorean identity is up here. We have 1 plus cotangent squared is equal to cosecant squared. So we actually didn't even need to have a thought bubble because cosecant x will stay the same, and then 1 plus cotangent squared x is just cosecant squared x. So we have one cosecant on the top, 2 cosecants on the bottom, which means we're going to reduce it to be 1 over cosecant of x, which 1 over cosecant of x is just, again, sine of x. That one was a little quick because we didn't really have to figure out this Pythagorean identity here. Okay, let's keep going. We only have 2 more, guys, okay, to do for these. So we have sine of x, and then we have cotangent of negative x. Well, if you remember, we have a cotangent right here of negative x, and that's going to give us, if we go back up to our even-odd identities, cotangent of negative x gives us negative cotangent x. So we're going to come down, and we're going to rewrite that. So we have sine of x times negative cotangent of x. Now, cotangent of x using our quotient identities is equal to negative cosine x over sine x. This is sine of x over 1, and we have a sine of x in the numerator, a sine of x in the denominator, which means this whole thing is going to reduce down to negative cosine x. Now, last but certainly not least, we have cotangent of pi over 2 minus x times cosine of x. Now, if you guys look back up to your, getting up there, if you guys look up to your cofunction identities, my goodness, I forgot what it was. Cotangent of pi over 2 minus x is just tangent of u. Okay, so we're going to bring that tangent down. I know I'm scrolling around a lot, I'm sorry. So we have tangent of x times cosine of x. Now, tangent of x using the quotient identities is sine of x over cosine of x times cosine of x. And that's really cosine of x over 1. So we have a cosine in the numerator and denominator. So this is just going to end up being sine of x. Now, I know we have a lot of sine of x's here. That doesn't always turn out that way. It just was trying to give you guys some good examples. Now, the last thing we can do is we can also use the fundamental trigonometric identities to factor and add trigonometric expressions. So these are a little bit trickier than the other guys, and this is why we also did a lot of factoring equations and why we also did some crazy fraction equations. So the first one I have here is cosecant squared x minus cotangent x minus 3. Now you notice that these are not the same trigonometric identities. We need to make them the same trig identities. And since we can't go from cotangent to cosecant, we can use a Pythagorean identity to make cosecant squared x into something containing a cotangent. So what I'm going to do is I'm going to go back up here to show you where we can find that. Under the Pythagorean identities, we know that cosecant squared x is equal to 1 plus cotangent squared x. So we're going to come back down, and we know that cosecant squared x is 1 plus cotangent squared x minus cotangent x minus 3. So now we're going to kind of put this in a correct order. So now we have cotangent squared x minus cotangent x. 1 plus negative 3 is negative 2. Now, because this is a trig function and has a lot of trig stuff in it, I bet a lot of you are going, I have no idea what we're doing right now, but let me just kind of make a side thought here. What if instead of cotangent squared x, you had x squared? And what if instead of cotangent x, you just had minus x minus 2? This is just a simple factoring equation, right? Because you're going to look for something that multiplies to negative 2 and adds to negative 1. And that would be negative 2 and positive 1. So we just factored that quick. So we actually replaced our cotangents here with just x. So now what we can actually do after we factored it, and this is a little trick that I learned, is now instead of putting the x in for cotangent, we're going to put the cotangent back in for x. So instead of x minus 2, now you have cotangent x minus 2, and instead of x plus 1, you're going to have cotangent x plus 1. And we have now factored this. Now that we factored it, we can actually solve for cotangent, but that's going to be a little bit later on in the chapter. The last thing we can do is we can add these nasty looking fractions here. Okay, and in order to do that, we actually need to find a common denominator. Now, the common denominator between 1 plus cosine x and sine of theta, I'm sorry, they're all thetas, is we're going to actually multiply them by the opposite denominator. So I'm going to have, and this is not going to look very pretty at first, we have sine over 1 plus cosine theta, and then we have cosine theta over sine theta. What I'm going to do is I'm going to multiply this guy over here by this denominator, so sine theta over sine of theta. I'm going to multiply this term over here by this denominator. So I have 1 plus cosine theta, 1 plus cosine theta. Okay, so now what we're going to do is we're going to simplify it all out. So sine times sine is going to be sine squared theta. And in the top, we're going to distribute. So we have cosine times 1 is just cosine. And then we have cosine times cosine is cosine squared theta. And again, this is all over the denominator of sine theta times 1 plus cosine theta. What do we do from here? Well, we're going to look for identities because this is a mess. But if you look, you have a sine squared theta and a cosine squared theta in your numerator. Sine squared theta plus cosine squared theta is a Pythagorean identity, and sine squared theta plus cosine squared theta is just 1. So now the top becomes 1 plus cosine theta over sine of theta times 1 plus cosine theta. And I think you guys may have already put 2 and 2 together here, but there's a 1 plus cosine theta in the top and a 1 plus cosine theta in the bottom. So now this becomes 1 over sine of theta, which, using a reciprocal identity, is just cosecant of theta. Much easier to use a cosecant theta than it is to use this fraction mess. And that's why we actually simplify trigonometric identities, is so that we can later solve them, and we'll be doing that in a couple of days. So that is actually the end of this unit. I will also post these notes up on Google Classroom so that you guys can see them. And if you guys have any questions, as always, you can email me or you can come to the Google Meet. I love explaining these. I'm happy to help. And if you don't have any questions, I hope you guys have a fantastic day.